In this example, we will be calculating a missing equilibrium concentration. So whenever you have the equilibrium constant and all but one equilibrium concentration. So in the previous example, we had in the part 1 video, we had only one equilibrium concentration. We were missing two of them. In this case, we have all but one, and the other equilibrium concentration will be calculated from this information and from the equilibrium constant. So here we have nitrogen oxides are air pollutants produced by the reaction of nitrogen and oxygen at high temperatures. At 2000 degrees C, the value of K for this reaction is 4 times 10 to the negative fourth. That shouldn't have two x's, it should just be one. And what we have to do here is calculate the equilibrium concentration of NO in the air at 2000 degrees C. The equilibrium concentrations of N2 and O2 are 0.036 molar and 0.0089 molar. So we have the equilibrium constant, and we have two concentrations, and we are just missing one of the equilibrium concentrations. So calculate overall, remember the main idea is that we're calculating one missing equilibrium concentration for this type of problem. So what do we have so far? We have the Kc that equals 4.1 times 10 to the negative fourth, no unit. We also have the concentrations of N2 and O2 at equilibrium. So these are the concentrations that we use to calculate the Kc. So to find our unknown, that one missing equilibrium concentration, we are going to go back to how we calculate this constant in the first place, this equilibrium constant. And remember, to do that, we take the products. In this case, we have that 2, that's why I put that 2 as a power, and then divided by the reactants. Both of the reactants just have coefficients of 1, so we don't have to raise them to any power. So let's highlight what we have and what we don't have. We have Kc right here. We have the concentration of N2 right here. And then we have the concentration of O2 right there. What we're missing is this right here. So we're just going to rearrange this. So some algebra again, coming back to haunt you again. And then solve for, x, which is the concentration of NO. So we are going to multiply both sides by N2O2. And then from that we get, obviously multiply it on this side. So N2 also multiply O2. I know that looks funky, but you know what I mean, hopefully. And this cancels out. What we're left with, and I'm going to flip it just so that we can see, it more clearly. So NO, the concentration of NO squared equals Kc times N2 times O2. So we have this so far, and it's looking good. Now, to get this concentration of NO by itself, we need to take away that square, right? So you see this little square right here? We need to take that away. To do that, we are going to do the square root on both sides. That square root cancels that square, and what we're left with is NO equals square root Kc times N2 concentration times O2. That's a times. And now we will be able to solve for the concentration of NO. And from there you just plug in, because we have all those unknowns. So it'll be Kc, which is 4.1 times 10 to the negative fourth, and I'm getting this from up here. And then times the concentration of N2, which is 0.0036, and then times the concentration of O2, which is 0.0089. And then you plug that into your calculator, and from that particular calculation, like under the square root, you should get 1.31. When you multiply those numbers out, you should get 1.31 times 10 to the negative 7th. And then when you take the square root of it, you will get NO equals 3.6 times 10 to the negative 4th. And in this case, you do have the units of mole per liter or molar, whichever one you want to say, but this is our answer. And you could actually go back and confirm by plugging all these concentrations in to this right here and seeing if you get that same Kc value of 4.1 times 10 to the negative 4th, and you will. So I won't do it here, but just know that you can confirm your answer in that way. Next, we saved the best, not really, because it's kind of difficult, challenging. We have this for last, so we have calculating equilibrium concentrations from initial concentrations. So this is, again, perhaps the most challenging type of calculation. And in this calculation, we will have some initial concentrations and an equilibrium constant. And this is the approach that we typically use. We will identify the direction in which the reaction will proceed first. So we've done this, part of this in that earlier example of an ice table. From there, we will develop the ice table and then calculate the concentration changes and follow that with calculating the equilibrium concentrations. And then we can confirm the calculated equilibrium concentrations. If you have made it to this video and to this last example, you're probably wondering, how will you test this, or how will this be tested on a quiz or an exam? I will keep it as simple as possible. I will probably only have like one of these equilibrium concentrations on the part where you show your work, on a problem where you have to show your work on the exam. So keep that in mind. I know you have constraint on time, but I do want you to learn how to do these, and it's important that you learn how to do them. So I actually omitted showing you how to do an even more in-depth calculation using algebra, an assumption of algebra. So we're just going to stick to this one where we actually solve for it. But keep that in mind. In the book, there is one final example. It's example 13.10, but we're sticking with up to 13.9. So let's go ahead and work on this. So this does have a lot of steps to it. So under certain conditions, the equilibrium constant Kc for this decomposition, so pay attention to that, decomposition of PCl5 into PCl3 and Cl2 is 0.0211. What are the equilibrium concentrations of PCl5, PCl3, and Cl2 in a mixture that initially contained only PCl5 at a concentration of 1? So what we're given here is the equilibrium constant right here and one initial concentration. That's it. So that is where this, ends up being the more challenging version of these problems. And the other ones, you're given, a lot more information, at least one or two more pieces of information. First, we are going to need to write out the equation, and we need to identify the direction in which the reaction will proceed to reach equilibrium. So first, start off by writing the equation. Now, luckily, this problem told us exactly what we need to know. We are seeing PCl5 decompose, so turn into, smaller products, and specifically they are PCl3 and Cl2. So we're starting off with PCl5 decomposing into PCl3 and Cl2 gas. Now, one thing I would recommend is checking if this is balanced. And in this case, we have, 5 chlorines on the reactant side, right here. And then we also have 3 and then 2 right here. So we have 5 chlorines on each side and then 1 phosphorus on each side. So we're good with balancing, but just, double check because the stoichiometry will affect the changes. So that's good to go. Now let's determine the direction in which the reaction will proceed. So we know that at the beginning, we don't have any products. yet, right? Remember, at the beginning of any reaction, you will not have any products at all. So because of that, you're going to proceed to make the products. So we know that this reaction will go to the right to start making products. Now we can start filling out our ice table, or setting up our ice table. So we all know what each of these stands for now. So initially, we are given one concentration. We are given the fact that the mixture initially contained only PCl5. So again, that's an important piece of wording because it lets you know how much of the the products you have. So of the reactant, we have 1.00 molar. Of the products, it's telling you initially you only had PCl5, you didn't have any product at all. So this is 0, this is 0 molar. So we have 0 for both of those. Now, we know that this reaction is going to the right. If it's going to the right, that means you are you're decomposing that initial reactant and you're forming, so you're increasing the concentration of the product. So we are losing, otherwise, negative, right, minus X of this reactant, and we are forming this much product. We're forming this much product. And again, it's X because we haven't figured it out yet. So this is what we have so far. And the fact that everything is 1-to-1, right? 1 PCl5 to 1 PCl3. That's why I don't have any numbers in front of those X's. But if you did, you would put those there. But in this case, everything's 1-to-1. So now we have that. Next, we have to fill in what we have for equilibrium. And by fill in, I mean we can just take the initial and either add or subtract whatever change it is. So for PCl5, it's 1 minus X. For PCl3, it's just X, right? 0 plus X just gives you X, and then 0 plus X just gives you X. So once we figure out that X, we will be able to figure out the unknown. So your next thing to do, we finished developing an ice table, we identified what the reaction was going to do. We are going to calculate the concentration changes by solving for X. So let's see what information we can use to do this. So we know that the equilibrium constant, and we have it actually, we know that the equilibrium constant is calculated in this way. The products divided by the reactants, well, the reactant, there's only one. And we know that it's equal to 0.0211. The problem told us that the equilibrium constant is equal to this. Because of this, we can fill in what we have so far from here. Remember that Kc always corresponds to concentrations at equilibrium. So we are going to use the fact that we have this equilibrium constant and we have these, changes filled in, represented by X or X's, to help us solve. So let's go ahead and fill in everything we have. So we know that overall, for PCl3, the concentration at equilibrium right now is just X. For Cl2, and what I'm doing is I'm like filling in this right here. And then for Cl2, it's also X, the concentration at equilibrium. For PCl5, the concentration at equilibrium is 1 minus X. Overall, this equals 0.0211. So we have that. Now, because of this, we can solve for X because we know what overall this equals to. So let's go ahead and simplify this a little bit more by just making it a little bit shorter. And I'm going to flip it around so that we can see everything better. So I'm going to put the 0.0211 on this side, and it equals to X squared, right? X times X is X squared. 1.00 minus X. It's a minus. So now what we can do is we can try and isolate that X. So first we are going to have to multiply both sides. So I'm multiplying 1.00 minus x there. And I'm also going to multiply it on the other side. So 1 minus x, multiply on that side too. So now we are actually going to solve this equation for 0. And we're doing that so that we can have all the x's on one side. That is our goal right now. So I'm going to rewrite just so we can see what's going on right now. So it's 1 minus x times 0.0211 equals x squared. That's what we have right now. We're going to subtract x squared from both sides, minus x squared. So then you have nothing there, it's just 0. So let's rewrite this again. So we have 1 minus x times 0.0211 minus x squared equals 0. And what we're trying to get at actually is, again, some algebra coming back to haunt you. We are trying to get to the form of, I'm going to write it up here so we don't get confused, ax squared plus bx plus c equals 0. So this is, you know, that equation, the quadratic equation. I think I'm saying that right. You can tell I'm not a math professor. This is the quadratic equation, and with this quadratic equation, we can actually solve for x using the quadratic formula. Yeah, another thing that we hate from algebra. So the quadratic formula is this. I don't know if you guys took a college algebra professor who showed you the song, but I'm not gonna sing it, but you should look up the quadratic formula song if you have never sung it before. So yeah, we're trying to get this equation right here in the form of that. So to do that, what we're gonna do is FOIL this out. So we need to FOIL this right here. This here and this here. And when you do that, what we're gonna get is, first of all, this first term will be 0.0211. When you FOIL out that first part, the 1 times the 0.0211. When you FOIL out the second part, we will get minus 0.0211x, right? And then that's FOILed out. We don't have to put anything in parentheses anymore. Minus x squared equals 0. We can rearrange this again, like I said, to get that quadratic formula form. So we are going to put minus x squared, and then we are going to include the x part. So we have this portion filled out. Now we need the bx, so the value with x and a number in front of it, which is this right here. So minus 0.0211x, and then finally just the number by itself, c, plus 0.211 equals 0. So I know this seems like a lot. This is one of the longer portions of the problem. So again, like I said, I will make it so that you have to know how to do this, but you won't have to sit there and do this entire process for an exam. You should be able to know how to do this for, you know, the BT assignment. If you want to turn that in with one of these problems, more than welcome to. And yeah, don't be intimidated so much by this. This is a learning process. Overall, what this teaches you is about equilibrium constants and equilibrium reactions and so on. Okay, so notice that here the x is a negative. We are going to flip everything so that it turns into a positive. So now we have x squared. That negative in front of the second term turns into a positive. So we multiplied everything by -1 basically. And then this right here is minus 0.0211. I'm getting tired of saying that number. Okay, so now we're finally ready. It's now in the form where we can plug in to the quadratic formula. So let's figure out our a, our b, and our c. So if you don't remember, the quadratic formula, the purpose of it is to find roots of x. So you're going to have two x values, and the quadratic formula helps you solve for both of those. So that's what we're going to solve for here. This formula is helping us solve for x. And remember, we need x to find those equilibrium concentrations. So that's why we have to do all of this for that. So A in this case equals 1. B in this case equals 0.0211. And then C equals negative 0.0211. So we have all of these, and we can plug them in to the quadratic formula. I know this is getting smaller and smaller. We're going to plug in. So first it's negative b, which would be negative 0.0211 plus or minus x equals negative b plus or minus. There I went. I sang it. I had to. The quadratic formula song. So then I plug in b again. And just know I hate listening to these again, so I probably won't listen to this one again, especially after me singing. Okay, and then for A, so I'm just following it. I'm just following this. I'm just plugging everything in according to what we determined, our A, B, and C. So our A is 1, and then our C is negative 0.0211. And then we're dividing the entire thing by 2a. So 2 times 1. So this is lengthy. You know, you're probably going to have to do it part by part in order to plug into your calculator, and that's okay. To simplify this a little bit more, let's just go ahead and, you know, square that one number under the square root. So I'm squaring that first part, that b squared, and you get 4.45 times 10 to the minus 4. And then for that second part, you get plus 8.44 times 10 to the minus 2. So we simplified those terms, and then at the bottom we can simplify it, and it's just 2. So that's a little bit more simplified. And then from there, you can actually, you know, plug it into your calculator. So I'll let you take care of that. If you do have any questions on how to plug this in, let me know. I would probably just add these two numbers first and then square them, and then do the plus and the minus. So you're going to go 2 routes here. One of them you're going to get a negative root, and then the other one you're going to get a positive root. So let's simplify that, everything under the square root. So to simplify that, we get 0.291. So it's negative 0.0211 plus or minus 0.0291 divided by 2. So like I said, you're going to get 2 roots from this. So one route that will give you a root will be the plus, and the other one is the minus. So one of the x's will be negative 0.0211, and this is just literally like review from college algebra, so you're probably sick of me right now, but it's okay. I'm not sick of you, so I'm gonna keep making these videos because I care about you guys and I want you guys to learn. This video is super long already and you can probably tell I'm like losing it because I'm just rambling. Anyway, a positive version and then a negative version. So this is the minus and this one's the plus. So you calculate these both out. For this answer, we get 0.135. For this answer, we get negative 0.156. From here, just know the negative doesn't make sense. That one we never take into account. Why does it not make sense? It does make sense because concentrations are either 0 or above, so 0 or positive. So for any time you have a root that gives you a negative number, that's not our answer. That's not the root we're looking for. The root we're looking for is the positive one. So this is our x. We solved for x finally. And now what we can do is go back to our original calculation, our ice table, and find the concentration. So X is equal to, and I'm gonna write it up here, 0.135. So we can remind ourselves, because I'm gonna zoom back in. So X is equal to 0.135. Now, going back, what are we doing? We're looking for the equilibrium concentrations of everything, of PCl5, PCl3, and Cl2 at equilibrium. So we need to find all of these. And we have, luckily, everything laid out for us. So for PCl5, so the concentration of PCl5 is equal to 1 minus X. We know that X is 0.135, so 1 minus 0.135, that gives us the concentration of PCl5 as 0.87 molar. We have 1 so far, and then the other ones are just X, so they equal exactly what X was. Remember that 0.135. So for PCl3, it's equal to 0.135. That's ugly, sorry about that. And then for Cl2, the concentration is equal again to just X, which is 0.135 molar. And yeah, I know this got messy, sorry. So these are our answers right here, what's being circled around in the yellow. So we did all of that just to solve for these concentrations. So again, this is the most difficult version of one of these problems. I will make it somehow so that it's not so long, but do learn how to calculate these. And let me know if you have any questions, and if you made it this far to the video, I applaud you. I know it was a long one, but I thank you for watching everything, because then I know that you're doing well at learning this material on your own, and you're taking that responsibility and learning how to calculate all of these things.